Okay, so again, here we are going to find the concave up or down. Our question said, is the graph f at x equal to x cubed minus 4x squared plus 3, whether it's concave up or down at the point. So the points have to be given to us. So A, we have 1 and 0. So the first thing we are going to do again, in order to find the second derivative, of course, we have to find the first derivative. We did the higher derivative already. So we find the first derivative, we get 3x squared minus 8x using the power rules. Then I have the first derivative, so I'm going to find the second derivative. It will give me 3 times 2, 6x minus 8. So we have our second derivative. Now I'm going to plug my x value. So the A, we have, I have student waiting. Okay, 1 second, please. Oh, that's okay. Nobody's waiting. Oh, so let me go back once. Okay, so here we find the first derivative, then the second derivative. Then now we are plugging, our point is 1 and 0, which means x is 1, y is 0, the point given to us. So we plug in the value of x in the function here. If it's 1, we will get 6 minus 8. 6 minus 8 is negative 2. Now, because the rule said if the second derivative value is less than 0, then the graph is what? Concave down. So our answer would be the graph is concave down. Now let's try the B if no question.
Oh, I have a question.
Yeah, go ahead.
So when you plugged in the first one, A, into the function, how did it end up becoming 3x squared when it started off as x cubed?
Oh yeah, that's what we said in the theory. You see, we have to find the first derivative, then we have to find the second derivative. F prime is the first derivative. F2 prime C, I hope you can see my cursor. This is the second derivative.
Oh, okay.
So in order to find, so the question said, a function is given to us. Always we know a function represents a graph. So the function given here, they say we should find where the function is concave up or down. Now, if they say we should find where the function is concave up or down, as we said earlier in the theory, let me go back one. For example, when we have this is our graph is the curve, and the line here is called a tangent. Now, when the line is on top of the curve, we say it's concave down. And then the opposite way, I'm going back just a second. Yeah, the opposite way. Now I have a curve open upward. The tangent line is below. When the tangent line is below the curve, it's called a concave up. So now, for example, a function is given to us. If we graph the function, it's easy. It's the same thing as we did the relative minima and maxima. If I graph the function, it's easy because I will see it right there. Yeah, when I know that the graph is open upward, then the tangent line should be down. So this will be concave up. So anytime we see a graph open upward, we are looking for at the point it's open upward, it will be concave up. If it open downward, it will be concave down. But the same concept as finding the relative maximum and minimum. For example, relative maximum means you are finding the point where the function increase and decrease, the point where it changes from increasing to decrease. But in order to do that, if you plot the graph, you will see all the point, you will see the shape right there. But we are using derivative to solve this problem. So this means I have to find the first derivative, find the critical point, then we do the step. The same concept here. In order to find this, we need to find the first derivative of the function, then find the second derivative of the function. Then the point is given. You substitute the point of the value of x. Now, if the answer is greater than 0, then it means it's concave up, less than 0, concave down. So that's the rule here. A function f is concave up on an interval. The interval will be given to you if the second derivative of the function at x is greater than 0. That's it. So we need to find the second derivative of the function. Then we plug in the x value. The point will be given to you, x and y point, but you plot only the x value. That's why they say f second derivative at x. And if the answer is greater than 0, then you say it's concave up. If it's less than 0, it's concave down. So that's what we did in this example. This is the function given to us. S cubed minus 4s squared plus 3. I need to find the second derivative of this function. Then I'm going to plot 1. X is 1, y is 0. I need only the x, so I'll plot 1. If the answer is less than 0, then I'll say concave down. If it's greater than 0, I'll say concave up. But if I'm plotting the graph, you can just plot this graph in your calculator, then you will see it right there. Look at the point, you will see it in your graph whether it's concave up. But again, here we are not using the graph, we're using derivative to answer this question. So that's why we get our first derivative. Here we use the power rule. S cubed will be 3s squared. 4s squared will be 2 times 4 is 8. 2 minus 1 is 1, so it will be 8x. So that's why we have 3s squared minus 8x. That's our first derivative. From first derivative, we go to second derivative. So we have to find the derivative of the first derivative. And that will give us second derivative. So 3 times 2 is 6. 2 minus 1 is 1. So we get 6x. Derivative of 8x will give us 8. Now we're almost done. We are going to, a means x is 1. So substitute 1 here. So we get 6 times 1 minus 8. That will give us minus 2. Since f second derivative at 1 point, the point is 1, it's negative value. So it's less than 0. Then we say it's concave down. And that's what we have here. It's negative 2. So it's concave down at the point given to us. Okay, let's do the second one. Again, the same process. So hopefully the second one we will get used to it. So let's try the second one. Since I'm using the same function, I already have the second derivative of the function. So this time I have 2 and negative 5. So I'm going to plug 2 at x. So 6 times 2 is 12. 12 minus 8 is 4. So I'll get a positive answer now. So that means at the point 2 and negative 5, the function is concave up because 2 times 6 is 12. 12 minus 8 is positive 4. And that's what we have here somewhere. Okay, that's right here. So 6 times 2 minus 8 is 4. So our answer is positive. So it's concave up. And you see when they plot the graph, everything show up here now. Everything show up. So for example, we are looking for 1. You see, this is 1 and 0. You see, this is, hopefully everybody can see where my cursor is. We can see that the tangent line is on top of the curve. So it's concave down. Then the next one is 2. You see 2 here down. So the tangent line is below the curve. So it's concave up. So anywhere the interval, you see the curve open upward, that will be concave up. If the curve open downward, in this case here, is concave down. So with the graph, again, we don't need to follow all the process. But again, here we are solving this problem by using derivative. And there's no any trick here. Always the steps are the same. Find the second derivative of the function, substitute the x value, If it's greater than 0, the second derivative of the s value is greater than 0, then it's concave up. If it's less than 0, then it's concave down. That's it. Oh, I have one student here. So if no question, let's keep going. Okay, so again, 2 examples is enough because again, there's no trick. Concavity, find second derivative, substitute the x point, less than 0, concave down, greater than 0, that's the second derivative of the s point, greater than 0, concave up. So next we move to the point of inflection. And we also said the whole theory of concavity is the tangent line. When the curve is open upward, the tangent line will surely be at below it. If it's open downward, the tangent line will be above it. So that's our main concern, where the tangent line will be above or below. In other words, at the interval where the function is open upward or open downward. If it's open downward, it's concave up. Open upward is concave up. Open downward is concave down. So next we'll move to the concept of point of inflection. The point of inflection, again, is where we have some changes. So here we changes of the concavity. So here we say a point where concavity changes is called the point of inflection. So again, a point where there will be a changes from upward to downward. Let's see if they give us graph here. Well, they didn't give it. Let's go back to the graph that, yeah. So here, well, by looking at this graph, where will be my point of inflection? It's where we have the changes of the graph open upward to downward, because the concavity is here. It's when it's open upward and downward. So that point will be around somewhere here where we see the upward open to downward open, the concavity. So that's the whole definition. A point SO and YO on the graph of a function is called the point of inflection. If only the curve is concave up on one side of the point and concave down on the other side. So where we go down and changing going up, between that point, we can see the left side is concave downward, the right side is concave upward. And the same concept, we have to find the second derivative of the function and also the point given to us. Then let's say the point is SO, we substitute SO. And it will be 0 or undefined. So here we say the point SO and YO, we have a point, always a point to have S and Y coordinate. On the graph of a function f is called the point of inflection. If the curve is concave up on one side of the point or concave down on the other side. But in order to know this, we have to find the second derivative at the point given to us. Now, if we find a second derivative and we substitute the point, the answer will be 0 or undefined. So let's see an example. Actually, this is a very good example here. I'm going to enlarge it, make it more bigger so we can see it well. I think it's okay. This looks perfect. Okay, let's go back. Yeah, this look okay. So this is the procedure, the steps here. But I'm not going to go through the procedure. We go through the example, it should be fine. So the question is given to us, find the point of inflection. And also, in order to get the point of inflection, we can automatically find the concavity also, because we know the point of inflection is where the concavity changes from up, down, down, up. So this question says we should find both the point of inflections. Again, we may have more than one point. It depends on the graph. If the graph curve maybe 3, 4, 5 times, we may have a lot of concavity. What I mean is that if it changes from upward to downward to upward to downward, a lot of concavity there. So the first thing we're going to do now, this is the function, x to the power 4 divided by 2 minus s cubed plus 5. The first thing we're going to do is to find the first derivative of the function. So I'm going to get 4s cubed divided by 2, and that will give me 2s cubed. So I'm using the power rule here. I get 2s cubed here. Then derivative of s cubed will give me 2s squared. And I have, 3s squared. We have cubed 3s squared. Then we know derivative of a constant value is 0. So this is our first derivative. Now we still need to find the second derivative. So the second derivative will give me 3 times 2 is 6s squared. 3 times 2 is 6x. Now the point given to us, in this case again, when we look at the definition, let's go. If you look at the definition, we say it's undefined or 0. So we equate our question, second derivative of the equation, we equate it to 0 to find the point. That will give us the point. So 6x squared minus 6x is the second derivative, equal to 0. So we factorize 6x squared minus 6x. The common value will be 6x, x minus 1. So the first value will be 6x equal to 0, x equal to 0 divided by 6. So the first point will be 0. X minus y equal to 0. X will give me positive, negative 1 across the equal sign to be positive 1. So s is 1. So this is the possible 2 points. We have the x 0 and 1. Now we say the second derivative of x is defined everywhere here. So that's again the first step. We find the second derivative. The second step, we equate the second derivative to 0 and we find the point of the x's. Now the third step, we have the 0 and 1. When we plug 0 into our original equation, we get 5 because 0 over 2 minus 0 will give us 0. So the first point to be, a point have 2 coordinates. So we only find the x. So we need to find the y. So we plug the 0 to not to the derivative of the function. You plot it to the original function. So 0 here, we get 5. So our first point is 0 and 5. Then the second, we have 1. If you plug 1 here, we get half. And we get 1 here also. So we get half minus 1 plus 5. And if you do the fraction, you get 9 over 2. 9 over 2. Now, here we say what? These are the potential points of inflection. We are not saying that. That's why here in step 2, we get 0 and 1. We say the second derivative is defined everywhere. But at the moment, we don't know the point of inflection yet. Now we need to test it. We're going to test. This is like finding the relative maximum and minimum in the interval. Remember, we used to test when it's positive or negative, then we make our decision. And when we look at the definition here, you can see that they test it with the second derivative, not the original function. When we are doing the relative minimum and maximum, we test it with original function. We find the first derivative, get the critical points, then get our interval. Then we test the interval with the original function. Here we test it with the second derivative. So you can see here second derivative. So I have 0 and 1, which means to my left can be negative infinity, to my right can be up to positive infinity. So to my left, I need to take any points here before 0 to test it.
Professor?
Yeah.
I see how it's x equals 1, but how is it x equals 0 as well?
Oh yeah, because when we have factorized a simple equation or finding a solution, I have 6x squared minus 6x equal to 0. I factorize it, I will get 6x. and s minus 1 equal to 0. So first 6x equal to 0 will give me 0. Then s minus 1 equal to 0 will give me 1. From
Oh,
here,
okay. Thank you.
yeah, okay. Since we have the second degree here, we get two s values. Okay, so far we did up to step 3. If it's okay, let me wait for a few seconds if we have question. Step 1, we find the second derivative. Step 2, we find the s point. Step 3, we find the point for both s and y. When we get s, we substitute s to the original function. Then we get the point, the y for both. But here they wrote potential point of inflection. We need to test because sometimes, if you can remember, when we are doing the interval of increasing and decreasing, sometimes a function may increasing and increasing again in the point, only that it will change the steepness, but from increasing to increasing. In a point of inflection, we want concave up to concave down, not concave up to concave up again. So that's why we need to test. So we test with the second derivative. I will take any value here. My point is 0 and 1. So to my left, it will be less than 0. To my right, it will be greater than 0. And in the middle, it will be between 0 and 1. So I may use a very small point. Let's say I'll use -1. I mean, you can use -20. You can use -99. You will get the same answer. It's best to use a smaller value so you can do the calculation very quick. So I will take -1 into my second derivative. -1 square will give me +1. 1 times 6 will give me 6. -1 times -6 will give me +6. So my answer will be +12. Okay, that's why they have positive here. So when it's positive, it means it's what? It's concave up. Remember the condition for concave up. Concave up means when you substitute the s value in the second derivative and the answer is greater than 0, then it's concave up. If it's less than 0, then it's concave down. So I'll take any point here, 0 to 1. Let me take maybe 0.1, 0.1 or 0.5, anything here. And when we substitute, I'm going to take 0.1. I think it's more better. So if I substitute 0.1 here, 0.1 square will give me 0.01, one more decimal place, times 6 will give me 0.06. So actually, I can say that when you substitute, when you find a square of a value that is less than 1, the answer will be smaller. If it's 1 or greater, the answer will be bigger. So luckily, the exponent here is 1. So here we can say that, let's say 0.1 square is 0.01. And then 0.1 to the power 1 is still 0.1. 0.1 is greater than 0.01. So this means the answer here will be negative. The right side will be bigger than the left side. So that's why we have negatives here. So this means it's concave down, negative. Then the last section, I'm going to use 2. Or you can use any value, +99, +1000. But I always try to use the most closest minimum value so you can do the calculation quick. So if I use 2, 2 squared is 4, 4 times 6 is 24. 2 times, okay, so this will give me +12. So I have positive. Okay, so this means all the 2 points here, they are all points of inflection, because points of inflection is where the graph change from concave up to concave down, down to up again. If like we get up, then the 0 is not a point of inflection if it's both up and up. Point of inflection is where the graph changes up to down or down to up. So our final answer will be, let me raise this up. We can see our final answer here will be both points, 0 and 5 and 1, 9 are point of inflection. But beginning, we say they are potential points of inflection because you have to do this test. Sometimes we may get up again, then that means 0 is not a point of inflection. So I'm going to wait for a few seconds if we have any question. So we can see that these steps is the same as finding the relative maximum and minimum the interval where it's increasing and decreasing is the same. The difference is that we don't find the second derivative. We find only the first derivative. When we find the first derivative, we equate it to 0, the same step, but we call it critical value, points. So there we get these points. Remember, we do this step in 10.1. When we get this point, we plug it to the function. Then we get the actual point like this. Then we test it where it's increasing and decreasing. Positive means the function is increasing. Negative means it's decreasing. And if I have from positive to increasing, then that's what we call the relative maximum, because it's to go up and down. Then from down up, it's called the relative minima. So again, 10.1 and 10.2, be careful not to confuse both. Point of inflection means we have to use the second derivative, and the steps are the same. Relative maximum and minimum means we have to use only the first derivative to find the x points. Okay, so if no question, let's keep going. So they plot the graph for us. So we can see the interval, we can see the change here. From 0 and 5, it goes, it's kind of like up, then it goes down a little bit here. So that's the point of inflection for those 2 points. Here we see changes from down, try to go up. Here from up, from down going up. But always very sliced, but you can see the shape. So we have another question example here. This time, this is application problem. And here they say that suppose that a real estate developer wishes to remove pollution from a small lake so that she can sell lakefront homes on a crystal clear lake. The graph in figure 10.18, again, this is from our textbook, shows the relationship between the dollars spent, the dollars to be the x-axis, on cleaning the lake, and also the purity of the water. So by looking at the graph, you can see that the more money we spend, the more the water is pure. But it doesn't go as a linear. It's not constant. It's kind of curving. Now, the question is, we don't see the question. They didn't ask a question here, but the question will be finding the point of inflection. But when we look at the graph, you can see they have C. C look like a point of inflection. It's kind of increasing very hard, but later on, kind of trying to, it's still increasing, but not the same rate as the first one. So let's see what the question is about. Now they say we should find the point of inflection on the graph, which is also, in this case, is called the point of diminishing returns. You see, the point of inflection from increasing going down. So it's a point of diminishing the returns on an investment, because it is where the rate of return or investment changes from increasing to decreasing. And looking at the graph here, we can see there is again increasing. It's kind of still increasing, but the steepness is kind of, there's difference between the two, the steepness. So if I'm investing, again, here we are talking about money. So if I'm investing money, I invest $10, I get 100% profit. I invest $20, I still get 100% or 200% profit. Then when I invest $50, I get only 50% in returns. Yeah. So I could say that my returns is diminishing. Still, I get positive. Based on this graph, I'm still getting a positive. I'm not losing money yet. If like the graph went all the way down, it means I should stop the investment. I'm spending more, but the purity is getting lesser. So that means I'm wasting money. It's increasing, but it's not, I'm not gaining good result as the beginning. So there is a diminishing of the returns. And that's what we're going to call the point of inflection. So we're going to follow the same step. We need to find the first derivative. The equation is not given to us, so the equation will be given to us soon. So we have to find the first derivative of the function. Then we find the second derivative, and we substitute the c. Based on the graph, we say the point of is the c. So let's say well, I think we are solving this question based on the graph. So let's go back and look at the graph well. So we are going to use the values here. So C will be our point. By just looking at the graph, we know there's a changes on C. And that's what they say we should look for. So the question says, look for the point of inflection on the graph at C, assuming F at C, then first derivative at C and the second derivative at C are defined. So we are looking, show that the rate of change in purity of the lake is maximus at this point. So after this point, this is the point where we get more, it's maximus, more returns. Below or above, it decreases. So if that's the case, here we say because S minus C is a point of inflection for F at X. We are C is here, so we are assuming this is our X axis. So S minus C is the point of inflection for F at S. We know that the concavity must also change at X equal to C. So if that's the case, then from the figure here, our goal is that we will say if S is less than C, then F at S will be concave up because the first derivative will be greater than 0. Because X is less than C, to the right, to the left, we can see there's more. Again, and the previous example we did, the function is given to us. By this question, we are using the graph to make our concept just by observing the graph. We can see that to the left, we can see the changes of the increasing. To the right of the C also, we can see the changes. So based on the changes, the original function F at X, not the secondary, the first function, is concave up. So the second derivative of F at S will be greater than 0. Then the second derivative is greater than 0 means that F at first derivative is increasing. The first derivative will be increasing. It have to be positive in increasing interval. So we say F at S is concave down. So the second derivative F at S will be less than 0. And if it's less than 0, that means the first derivative is decreasing. Again, based on this question, we are the function is not given. We are in this section going, we are giving all the possible conditions. There's two conditions, either concave up, concave down, or the first derivative. Remember, we do that. When we use the first derivative, we are looking for the interval where it's increasing or decreasing. So here we are not solving problem, but we're just giving the conditions. The first condition said if X is less than C, then F at S will concave up, of course, because C is greater. In that case, the second derivative then should be greater than 0. But if the second derivative is greater than 0, this means that interval function will be increasing. So the first derivative will be increasing. Or the opposite. If S is greater than C, then F at S will concave down. And second derivative at X will be less than 0. If it's less than 0, it means the first derivative of it will be decreasing interval. We get a decreasing. It's going down up or up down. So what we just, the two rules here is just the theory. from the theory, we know concave up means the function is doing what? Is increasing to decrease. Concave down means what? From increasing to decrease and decreasing to increase. Let me go back to the theory for us to understand. Hopefully, well, let me use this graph. For example, this will be at my concave down. It means the interval is from what? Increasing to decreasing. Concave up means what? From decreasing to increasing. So this will be concave up. And we know this point means relative minimum. Relative minimum is when the function is from decreasing to increasing. Relative maximum means from increasing to decreasing. So those just these are the theory that we are stating here right now. We are not solving any problem. The function is not giving. So those are the two theory. So we said that if the first derivative at x as first derivative at c, then it has what we call the relative maximum. Because relative maximum is what? From increasing point to decreasing. In that case, we're going to get what? Concave down. So that's the whole concept. Again, we are not solving a problem here because the function is not given. We are just stating the theory, the conditions. There's two conditions here. Either c is greater than x or is less than x. Then we lay our possible two answers. And that's what we did here. Also, we can do what we call the second derivative test. So for example, here we say we can use information about points of inflection and concavity to help sketch a graph. So for example, if we know that the curve is concave up at a critical point where the first derivative f at s equal to, remember the critical point is where we know whether the function, the point where the function is increasing to decreasing or decreasing to increasing. So what we are trying to do here is that if we can find, we are not going to graph the whole, for example, if I'm going to graph a function, maybe I may need a lot of points to plot and see the shape. But if we use a second derivative test, we can get the idea of the shape of the graph. First, we will know second derivative test will give us whether the function is open upward or downward, based on whether it's concave up and down. Then we need to find a critical point where the function is increasing and decreasing. So those are the two major points, and that can give us the shape of the graph. So, for example, in this case, we will see that this graph is what? Open downward. So this point here will be our relative maximum. So if we know the critical point and we find the relative maximum, which means from increasing to decreasing point. Also, that will give us the concave down. And how do we know it's a concave down? We will test with the second derivative of the function with the point, the same point we can use, or use any point where the tangent line is above the curve, and it should be again either positive or negative, concave up or down. So we have an example here how we can see the shape of this graph. I'm going to make this very big. So here we are doing the second derivative test. So the question here says find the relative maxima and minima of this function. So the first thing we do again find the first derivative, the same step. The answer we get, then we find the x points. So here we get s, again, this is the function. The first derivative will be s squared minus 2s minus 3. Then we know we can factorize this to find the x. So we get s minus 3, s plus 1. We find two values. When we multiply, we get minus 3. When we combine, we get minus 2. So minus 3 times plus 1 will give me minus 3. Minus 3 plus 1 will give me minus 2. So these are the. So from here, we can see that s equal to 3 and also s equal to negative 1. So negative 1 and 3. Then here also we say no value of s make the first derivative of s undefined. Yes, because a polynomial function, the function will always exist from negative infinity to positive infinity. The two things we have to consider whether a function is undefined is when we divide, the function is divided by 0, it's undefined, or square root of a negative value. So anytime you have a function that it doesn't have no square root, it doesn't have no division, that means the function will exist from negative to positive infinity. There is no undefined place. So the next step is we want to get the second point, which is the y. So we start with the negative 1 first. When we plug negative 1 to the original function, we get 11 by 3. We plot the 3 to the original function, we get negative 7. So this is our critical point, negative 1, 11 by 3, 3. So almost the same step, we find the relative maximum and minimum. But here we are looking for relative maxima. Maxima means only one point, the highest point and the lowest point. So the next step, we find the second derivative. And this is the second derivative of the function. Base here to be 2s minus 2. Then we are going to test the same points, negative 1 and negative 7. So negative 1, we get negative 4. When we plug negative 1, it will give us negative 4, which is less than 0. So we'll say that negative 1 and 11 by 3 for the second derivative section is relative maximum. Because relative maximum also gives us what? The concave down, the same concept. Because remember, with the concave down, we test the second derivative with the point. And if it's less than 0, then it's concave down. If it's greater than 0, concave up. And let's go back here. If I have this graph here, this will be concave down. And also the point here is what? It's relative maximum. Relative maximum means from increasing to decreasing interval. So that's why here we are saying it's both concrete. I say concrete. It's both concave down or relative maximum. Then we test the second point, which is 3. When we plug 3, the answer is greater than 0. The second derivative is greater than 0. So this means it's concave down. When it's concave down, it means the down point. So it's a relative minimum point. And they say the graph is shown here. So we can see the graph here. So we can see our relative minimum point. And also we call it concave up because it's open upward. The top, negative 1 and 11 by 3 is relative maximum, but it's concave down because it's open downward. So that's our second derivative test. We can, when we find the relative maximum and minimum, we can still do the second derivative test to see if it's concave up or downward also. Always relative maximum, it should concave downward. Maximum is at the top. the tangent line will be on top of the curve.
Can you go back quickly, Professor? No, to the one before that. Thank you.
Okay, so if no question, let's skip. Again, if you have the book, the same concept, the book also take time, explain it. This example straight from the book. So yeah, they say we should compare the advantages and disadvantage of second derivative tests. Well, it's very quick and easy for many functions. But we should be careful. The second derivative is difficult to find some of the functions. Also, the second derivative test sometimes fail to give a result, so we have to be careful. It's not even advisable to plot or to predict a shape of a graph using concave up and down or using basically the second derivative test. I mean, it's something we should know because it's very quick and easy, but not for all functions. For some functions that are very complex, we may fail to get a good result. So let's say this example, concavity from a graph of y equal to f derivative at x. So we have a question here. They gave us the graph already, 10.25. And this graph shows the first derivative is given to us. And now we are not doing antiderivative yet. Like we can, we can find the original function. I think this will be chapter 12. We can find the original function from the first derivative. But right now we don't need it. Actually, they already solved one step for us, so we don't want to go back to the original function. We have to, concavity means we need second derivative. So the function, the first derivative of the function is given to us. The graph also is given just for us to see the shape. And maybe from this we can verify our result. If we are looking for the concavity, this graph means it's at the top. It's open downward. So the tangent line on top means concave down. And this will be a relative maximum also from increasing to decreasing. So we can find the interval of increasing somewhere around here in the middle. To my left is increasing, to my right is decreasing. So the question said we should find the interval on which f at s is concave down or concave up. So we need to find the second derivative. We have the first already. Then we should find the s value at which f at s has a point of inflection. We're still going to use the second derivative. Then check the conclusion from part A and B by finding the second derivative and graphing it. So again, you can use your calculator to graph it. That's the fastest way to do it. Don't do it manually. Then D, f at x equal to 1/3 9 minus s cubed. And this, calculate the first derivative, verify that this could be f at x. So we just have to find the first derivative of this function if it will be the function f at x. So let's start with A. The A, we are going to find the interval where the function is concave down or up. So concavity for f at x can be found from the sign of, as we said, the second derivative. When we get the second derivative, we point the point. If we have a value greater than 0 or positive, then we say it's concave up. If it's negative, concave down. Now, because the second derivative is the first derivative of the first derivative, which is given to us, whenever the graph is this increase, it follows that f second derivative also be greater than 0. If the graph is increasing the first derivative, then we have concave up. So we find the second derivative of the function. If it's greater than 0, then we say again it's concave up. If it's less than 0, we say it's concave down. So I'll wait for a few seconds, see if it's okay, the first section. You see that here we solve this problem very quick. We are using the second derivative test. Instead of finding the second derivative of the function, then you have to find the point of inflection. We are just testing it because we know if the first derivative is increasing, then the second derivative will be of the first derivative is increasing, which is given to us. They give us the first derivative, and we saw the increasing section. So if the first derivative is given anything, we don't need to find the function. For example, second derivative will give me negative 2s minus 2. Then I'll use that to find the rest of the s point. Then I'll plug it to the original function to find both s and y to make it 1 point coordinate. Then I'll use it to test. You don't need to do all that step. So we say the concavity of f at s can be found from the sign of second derivative. But because the second derivative at x is the first derivative of the first derivative at s, whenever the first derivative increases, it follows that the second derivative also will be greater than 0. Or the other way, here we say it's greater than 0, f at s will be concave up. If it's less than 0, then f at s will concave down. So that will be our solution. That's it. We don't need to follow all that. That's why they say the advantage here again, it works for this function. This is a very simple function, and it's very quick and easy than following all the 4 steps. Now in B, let's see what B said. B said we should find s value at which f at s has a point of inflection. So from A, we just find A, we know that second derivative at x changes sign at s equal to -1, because less than -1, we have concave down, greater than -1, no, sorry, greater than -1, we have concave down, and less than -1, we have concave up. So which means the point of inflection, we have changes at the point at -1 is where the changes occurs. So we say the second derivative changes when s is -1. So f at s has a point of inflection at s equal to -1. So we should note that the first derivative at x will have its maximum point, or the maximum at x value, when f at s has a point of inflection. So point of inflection is again where we have the changes of up to down. Points of inflection for f at s will correspond to the relative extrema. The relative extrema will be either relative maximum or minima for the first derivative f at x. And now for C, they say we should check the conclusion from part A and B by finding the second derivative and graph it. Then D, we are going to find the derivative of that function, the first derivative, to verify it. But again, here we have to use the calculator. So again, they graph it here. This is the function. And the second derivative will give me -2s minus 2. So figure 10 point show the graph of the second derivative. Remember, second derivative, the highest degree of x is what? 1. So you have to be a linear equation. You have to be linear. Again, you can use the calculator for this to graph it. Or you can plug in a 2 points, since the first derivative is s squared, so it will look like, it will be a parabola. And since it's negative s squared minus 2x, this is a quadratic. So when we look at the graph, we can see it's a parabola. And also it's open downward because it's negative value. And the coefficient, this is like quadratic. Let's go back. Maybe we did this in pre-calculus. If I have a quadratic equation and the coefficient of the highest degree S square is negative, it will open downward. Positive, it will open upward. So just by looking at the graph, we can know the shape. But if we have the highest degree is 1, it's a linear function, it's a straight line. So that will be our conclusion of A and B, parabola and linear. And D, they say we should find the derivative of this function. And then we should conclude whether it's the same as the one we have. So here we have 1/3. Derivative of a constant value is 0. Derivative of negative S cubed will give me negative 3S squared. Derivative of negative 3S squared will give me 2 times 3, which is 6. The negative value, we keep it. Then let's simplify this equation. 3 will divide both terms. So that's right. Remember our question gave us the first derivative of the function should be negative S squared minus 2S. So we conclude it's the same. It's the same function first, it's the same first derivative function. Again, the future chapter 12, we're going to find the original. Here we are not looking for the original function, but we can also find the original function here. By using this, we can come back to the top here, but that will be the different topic of antiderivative or integration. And that will be our last chapter of the course. So this is the graph here, because we have a S cube, the highest degree. So we can see the graph is have 2 turning points, S cube. So this is the original function now. The original function, the shape of the graph, we have 2 turns. Relative maximum and minimum is here. But when we find the first derivative, the degree reduced to 2. So we have only 1 turn. And this time we have only relative maximum. It turn open upward. Then when we find the second derivative, the highest degree of the S was 1. So it turned to only one linear, it turned to a linear function. So the relationship among f at x, first derivative at x and second derivative at x that we explore in example 6 is what is in the table here. So remember, f at s, we're looking for concave up, concave down, or point of inflection. Well, let's start with the concave up. The first derivative, we will get an increasing. The second derivative, the testing will be positive. Concave down, we get decreasing, and it will be negative. Point of inflection from maximum to minimum, from positive to negative will be maximum, and from negative to positive, because point of inflection is where we change from concave up to down. So maximum of point of inflection is positive is concave up, negative is down. So from concave up to concave down is called the maximum. Then concave down to up will be the minimum for the first derivative. Remember, if I'm going concave up to down, I'll get relative again maximum, or the other way minimum. So that will be the conclusion for our section here. Again, this is one of the longest chapter section for the textbook. So today we are going to do only 10.2. Actually, our time is gone. Okay. So that will be the conclusion. So hopefully on Thursday, we're going to cover point 3 and point 4. Point 2 is a very long chapter. long section of the chapter. So any question before we leave? Again, we have a homework due today. The next week homework also cover only 10.1. It doesn't cover 10.2 yet. So hopefully we will see homework soon that will cover 10.2 and 10.3, hopefully. So if no question, then we are going to end here. Let me stop the recording. Hopefully I'm going to post the recording in tonight or tomorrow.